first law of thermodynamics can be expressed mathematically. The total change in the internal energy is the difference between the final internal energy value and the internal energy value, that is, delta U equals UF minus UI. Energy conservation requires that the total change in internal energy from its initial to its final equilibrium conditions be equal to the net transfer of energy, both as heat and work. This statement of energy conservation is the first law of thermodynamics. Delta U equals Q minus W, or the change in the system's internal energy equals energy transferred to or from the system as heat minus energy transferred to or from the system as work. In a cyclic process, the system's properties at the end of the process are identical to the system's properties before the process took place. The final initial values of internal energy are the same, and the change in its internal energy is zero. So delta U net equals 0 and Q net equals work net. A cyclic process resembles an isothermal process in that all energy is transferred as work and heat. But now the process is repeated with no net change in the system's internal energy.
What should happen is Jesse's going to take this smaller pot, which is boiling, and he's going to put it in the bigger pot that is also boiling, and the smaller pot is going to stop boiling. So as you can see, the smaller pot is no longer boiling, and the big pot is still boiling. So
that's actually really cool. Sweet.
W net equals Q net QH QC. This is the formula obtained from the first law of thermodynamics. It is indicated that all the energy entering and leaving the system is accounted for and is thus converted. The second law of thermodynamics states that a heat engine cannot transfer all energy as heat to do work. A heat engine carries some substance through a cylindrical process during which, 1, the substance absorbs energy as heat from the high temperature reservoir, 2, work is done by the engine, and 3, energy is expelled as heat to a lower temperature reservoir. All heat engines operating in the cycle must expel some energy to a lower temperature reservoir. Therefore, it is impossible to construct a heat engine that operates in a cycle, absorbs energy from a hot reservoir, and does an equivalent amount of work. The requirement that a heat engine gives up some energy at a lower temperature in order to do work does not follow from the first law of thermodynamics. This requirement is the basis of what is called the second law of thermodynamics. The second law of thermodynamics can be stated as follows. No cylindrical process that converts heat entirely into work is possible. According to the second law of thermodynamics, W can never be equal to QH in a cylindrical process. In other words, some energy must always be transferred as heat to the system's surroundings. A cyclic process cannot completely convert energy transferred as heat into work, nor can it transfer energy as heat from the lower temperature body to a high temperature body, without work being done in the process. A measure of how well an engine operates is given by the engine's efficiency. Efficiency is a measurement of the useful energy taken out of the process relative to the total energy that is put into the process. For a heat engine, the efficiency is the ratio of work done by the engine to the energy added to the system as heat during cycle. And then there is the equation is basically just the simplest is 1 minus QC, which is the net work done by the engine, over QH, the QC is energy removed as heat, and then over energy added as heat.
okay. Ready?
Yeah.
Yeah! As long as forces inside and outside are balanced and equal from the can and the outside of the can, then nothing changes on the can and it all stays the same. But when the forces are unbalanced, changes in the shape of the metal container will take place because of it's trying to get back to equilibrium.
Yeah!
That's the second law of thermodynamics.
Dynamics, a system left to itself tends to go from a state with a very disordered set of engine, one that has only a small probability of being randomly formed, to one in which there is a less order, or that has a high probability of being randomly formed. The measure of a system's disorder is called the entropy of the system. The greater the entropy of a system is, the greater the disorder. The greater probability of disordered arrangement indicated that an ordered system is likely to become disordered. Put another way, the entropy of a system tends to increase. The greater probability also reduces the chance that a disordered system will become ordered at random. Thus, once a system has reached a state of greatest disorder, it will end to remain in that state and have maximum entropy. Greater disorder means there is less energy to do work. Because of a system's entropy, it is the ability to do work and the direction of the energy transfer. The second law of thermodynamics can also be expressed in terms of entropy change. This law applies to the entire universe, not only to a system that interacts with its environment, so the second law can be stated as follows. The entropy of the universe increases in all natural processes.
Okay, so right now this deck of cards has very low entropy because it's very well ordered. So if I were to just pick some cards out of the deck at random, which is harder than it looks. Okay, so now it's more disorganized, so it has more entropy than it did when it was just in a nice orderly deck. And then it gained even more and more entropy if I started just like throwing the cards on the ground. Because now there's no order at all, so the entropy is a lot higher. So, put another way, the entropy of a system tends to increase. Any movement you do to these cards, the entropy is going to go up because it's not as perfect as this. So, the greater probability also reduces the change that a disordered system will become ordered at random, meaning the cards that are on the ground right now aren't magically going to come and be part of a nice orderly deck again. That's not going to happen. So, once a system has reached a state of greatest disorder, it will tend to remain in that state and will have maximum entropy. So all the cards on the ground is maximum and it can't go back to be normal.